Okay, so first little caveat, I want to explain what I'm going to be talking about in the presentation. So this was actually kind of my first real experience with deep learning. My goal is to find a practical application to kind of like actually use it instead of just doing like a toy problem. I read a lot about like imminence, and I'll go over that stuff, and different like, you know, classifying cats and dogs and things like that. But I wanted to use try to come up with a real world robotics problem. And this was actually kind of difficult. There's a bit of a learning curve, and I have been reading about deep learning and actually read a couple books on it over the past couple of years, kind of getting ready to do this. So I don't want to discourage anybody, but expect a little steep learning curve at first. Though once I got past that, it was kind of interesting to start to play around with the models and rerun them and improve on stuff. So I'm going to touch on theory, though this is such a deep subject and so involved, I can't really do it justice. So I'm going to give some recommendations of some follow-up afterwards, and then I'm going to really show, we're going to show a demo of deep learning in action and kind of explain how I did this project. Just to give a little preview, the project is a thermal camera. I got a thermal camera from Adafruit, and I wanted to detect wet spots on carpeting. So I went around and took pictures of that, and then created a deep learning model to do detection, and hopefully I'll do a live demo, and it may or may not work. It's a little hit or miss, but you'll see it in action. So just a quick definition. So deep learning is a form of machine learning. So it's basically a way to, instead of hard coding rules into a computer system, a way to show a computer examples of outcomes, and then to have it kind of tweak and figure out what the, to have it discover the algorithm for itself. Let's see. Okay, so I'm going to go over some of the components. So the first basic component of a neural network, and if we get too technical, I'm also going to give a little caveat. Maybe Craig can jump in with if you have any like real, because I know you did like your master's on deep learning, so you can answer any of the math questions. Before I jump in that, there is a significant amount of math, but it's also interesting. You don't actually have to really understand the math to use deep learning. You have to know like when it's appropriate to use specific algorithms, and you can apply the different algorithms and experiment with them, but you don't actually have to understand how they work unless you're like reinventing the libraries. So first part is a perceptron. So the perceptron is I guess it'd be a kind of a mathematical formula or an algorithm that's kind of based on the human neuron, or human brain cell. And so if we look at a brain cell, so we have the actual cell itself, and the cell has dendrites, which are the inputs. So the inputs to our perceptron, which is our math formula or our algorithm, so those would be our x's coming in. So we have multiple inputs or multiple features. So if you're looking at a picture, you have pixels. Now each pixel would be, you know, the top left pixel could be x1, and the next pixel will be x2 and x3, and so on. The formula to activate that cell, or to pass that information on, is just a simple summing of the cell, or summing of the weights coming in on the dendrites. So the weights on the inputs are just 0 to 1, or they can actually be negatives, though they mostly use positives now. So you're just multiplying that x by an input, you're summing all those inputs together and adding a bias. And a bias is just another simple, just a number, an integer or something, or a floating point. And then that becomes your activation threshold. That goes through activation function, and the activation function is usually just converting that. So the number can be like a large number, it can be like 20 or 30 or 50 or something. But for most of these formulas to work well, we really need a number between like 0 and 1. Like I said, sometimes they use negatives too, but I've seen that most of the modern formulas actually have avoided using negative numbers, and they're using much simpler activation functions that just, in fact, the one that's really popular right now, just as simple, is a max function. It's just, if it's below 0, then it's 0, and if it's above 1, then it's 1, and then if it's in between there, then it's whatever number. And it's a real simple way of passing that information from one perceptron to the next perceptron. Okay. So this is another image of the algorithm and the way it works. So we have all our x's, which are features. In the case that I'm going to be showing you, it's a thermal camera. So those x inputs are actually going to be temperatures. So we're taking the temperatures and we're multiplying them by the weights, which is W, and then you're summing them up. So the interesting part about this is, so we know the x's, so that's our inputs, and we know, will know the outputs for our training data. So when I have an image, or I have a bunch of thermal information, temperature readings, I know what the output is, because when I took the picture, or it's not really a picture, but it's the readings. When I took the readings, I actually label that information. So I end up with a bunch of labeled data. What I don't know is what these weights should be to ensure that new information being passed through the weights and biases will get the old information. So that's the process that the computer is going to actually experiment with different weights and biases, and it's going to run through a learning process, which I'll show later also, and hopefully output the correct answer. Okay. So yeah, when I first started looking into it, there's a lot of different activation functions, and for different problems it may be important, like a 0 to 1 max, like ReLU, this is one I use for my problem, may not be best, but for the majority of problems it's pretty fast and pretty effective, so it's the one you should use. But these are one of the things you can tweak in your model, is to try to choose different activation functions when you're creating the model. And I'll show you where you can do that too. It's pretty straightforward, because most of these are really built in to TensorFlow and the libraries, and you can just literally name them and pick different ones and do experiments.
Sigmoid is the most current, or the one that you typically use.
Give you a comment on that, Josh?
What?
Can I give you a comment on
Yeah,
that?
go ahead.
So, for what he showed, that perceptron, it's almost by definition a binary output. A bunch of inputs will give you a yes or no answer, or an on or off answer. So that step function is effective because it's by definition yes or no. When you go into full neural networks, which is clusters of perceptrons hooked to each other in layers, often what you want to, if you put that step function in there, it becomes very erratic. It'll go from no, or it'll go from, when you're doing full neural networks, you're not doing typically yes, no's. You're doing degree of membership. So you want to know, maybe you're doing a robot and you want to turn left. Well, how far left? Do I turn 10 degrees? Do I turn 45 degrees with my wheels? A full neural net can give you that proportional analog difference, right? Well, you don't want it just to go 0, 0, 0, 0, 0 all the way left, right, which a single perceptron would do. The activation function of a sigmoid will give you a lot of inputs to a lot of outputs, maybe a bunch of inputs to a 10-bit analog or digital out number that represents your analog to digital threshold, or your digital analog threshold, how far you want to turn analog wise. A step function in that scenario will make it very jerky, because each individual perceptron will jump up or down, kind of erratically, and what they add up to then in the end can be a radical number. The sigmoid function makes it more smooth. Because if you're kind of in that transition area, you don't add a whole 1 to the number, but you're saying, yeah, I'm kind of getting there. And if a whole bunch of neurons kind of get there, then it'll add up to more. Does that make sense?
Yeah.
And
It
so,
really depends on, like you said, the application. In
Yeah.
that sense, if you're using it for a steering robot, the application would be the best Sigmoid. But if you're trying, maybe because he's just classifying images and it's
Yeah.
like a yes or no, then it's up to, his, the weights.
yeah, it'll work fine. If the difference between 0 and 1 made a difference to him, then that binary number, that binary step function wouldn't give him in-betweens. It would just oscillate between zeros and ones.
Yeah.
And something like a sigmoid function would be kind of in between, it would rise and fall more gently.
So for this talk, though, I didn't want to focus too much on the theory and the choices between them, because there's a lot of great stuff out there on deep learning. There's so much information. If you go on YouTube and watch videos, and there's books on it. I kind of want to gloss over this stuff kind of quick, just make sure we have a general vocabulary, and then go into the stuff that I found that after using the tutorials and reading them, they didn't really explain really well, like how to load your data into the models and how to clean your data up and things like that. So, okay, so one of the last parts is your loss or cost function. So when you're feeding this data in and you have predictions, so the classic cat dog example. So I'm feeding in pictures of cats and I'm feeding in pictures of dogs. I'm getting outputs. So the outputs I'm getting are numbers between, so for the cat it's 0 to 1 or the dog is 0 to 1. 1 being 100% sure it's a cat and 1 on the dog being 100% sure it's a dog. So to give some feedback to the system of whether it's correct, we have a loss function. So instead of doing this simple linear loss function, like if we have, it says, oh, I'm 50% sure it's a cat, and it's wrong, then the loss would be 0.5. It turns out to be faster to train the models if you use like a logarithmic loss function, or I think most popular right now seems like be a mean squared error. And that means that the low losses cost less and aren't considered that big of a deal. So there's no, you don't want to significantly retrain your model for small losses, but higher losses go up exponentially, and then it would re-weight the model more strongly for that loss. So, okay. All right, so the last step, which is kind of the complicated magic of the whole thing, is gradient descent. So anytime you're trying to determine what something is, you end up with like features that you can graph them out. You have x, y coordinate. It's sort of a little more complicated. So this is x, y, z coordinate. So if I have features that come in, this is my loss function calculation. So up higher is a very high loss, so it did a poor job of recognizing what it is, and down low would be a very low cost or low loss, so it does a good job of recognizing what it is. So gradient descent is the method that's used of adjusting the weights and biases to reduce the loss or cost of the algorithm that's used that determines what that object was, or classify it, or whatever it's doing. So gradient descent is another thing that it uses some calculus, but you don't actually have to know how it works. You just have to apply a gradient descent optimizer to your model. I'll show that in the code.
About that.
Yeah.
Is there a problem, because you're trying to, I think, you're trying to adjust weights of all these different inputs. So is there a chance that you're going to start going off and find, for example, a local minimum that really isn't the one you wanted, but now
Yes.
you're down here,
Yeah.
it looks like you're.
Maybe I should put up a simpler graph, but sometimes, just imagine I'm drawing a graph like this. It goes up and down like a roller coaster, right? So I have different hills and I have different valleys in my graph. So yeah, you have what's called a learning rate that you can apply to your to the gradient descent algorithm, and so it can get stuck in what's called a local minimum. That it finds a good loss because it finds one of these higher valleys, but it doesn't know to go over this next hill down to the lower valley and keep looking. So that's kind of a tough problem. A couple ways to deal with it. One, these are a little bit random. They actually randomly start with different weights and values. So sometimes you running the training just gets lucky because it starts at a randomly good spot and you just get a better result. They also use, everybody really uses, instead of the gradient descent algorithm, they use what's called atom optimizer now, which is what I was also using. I started with the gradient descent and I switched to that. I think it's just a form of gradient descent, but instead of giving it a fixed learning rate, it modifies the learning rate as it trains. So it kind of does a search with a large learning rate where it's jumping around, you know, making big jumps from one location to another, and then as it hones in, it shrinks the learning rate down to find the optimal answer. So when you look at these problems, and I'll show you, one is going to show you the size of the issue. Finding the optimal answers is really a little bit of luck with everything, because there's just so many weights and so many biases that have to be adjusted. You just can't brute force through them all. So you just,
And it's also about
Yeah.
your training data, you know, how well your training data is opposed to what you're actually looking at.
yeah, training day is very
Environment
important.
is a
It's
big
one of the
deal.
things I
mean,
found
there's
out.
a lot to deal with, the resolution of your camera, frame rate, yeah. But you obviously have to do an act to where you can kind of optimize it to where you expect a certain degree of confidence.
Okay.
What kind of resolution is on that thermal camera, by the way?
The thermal camera is 8x8,
Are you using?
very low.
There's a machine vision plug-in for that. You can sub-pixel it and get it to a much higher resolution,
I use it on the display,
but not on the data.
not on the data. Although I did think about that. I wasn't sure if it would be better or not to do
May not be, because sometimes you can. add more,
interpolation.
but-
Yeah, because it's fake information. But yeah, I'll go over that when we go over the code.
Okay.
So, but yeah, I did think about that a little bit. So this is a DNN, which is deep neural network. So this is one style of neural network. There's actually a lot of ways to arrange perceptrons, and this is actually an older method, which is used in a lot of basic examples. And I actually got a little bit of a false start because I didn't realize this was not necessarily the recommended way of doing things, and I got decent, okay results with it, but I switched to a new one later that worked much better. So in this one, there's these are your perceptrons that I talked about earlier, and coming out of the perceptrons, they are connected to every other layer of perceptrons. Each of these lines indicates a weight, so that's going to be your W values, what you multiply your input. So your first input layer, in our case, these are going to be temperature readings. So I have 64 temperature readings. And then you'll pass those to the next layer, which will then multiply that by weights. And then the next layer in this one is dropout, which I also found was kind of important to use. One of the problems you get with neural networks is they can become essentially memory banks. So you feed your images in, and it adjusts all these weights and biases to give you the right answer. And eventually, after training for a while, it just completely remembers.
Memorize the training set.
It memorizes the training set, and it doesn't work at all in the real world examples. So this is what's called overfitting. And if you graph it out, probably another graph I should have had. It'd be like if I had a bunch of dots I was trying to graph, and they went gently up a slope, and my best line would be this line, and I overfit it, and the computer instead decides that my line looks like this, and it hits all of my points exactly instead of figuring out a
There's some
general line.
ways too to look at the error as you're training and know when to stop.
Yeah.
That you can use, the heuristics that.
So one of the popular methods right now is called dropout. So what you do is you can apply a percentage. So what it does is when it trains, it's going through this neural network over and over and over again. Every step, it's retraining, trying new weights, trying new biases, calculating new lofts every time. And then what we can do is randomly basically kill the perceptrons. So that's a dropout. You can just get rid of a percentage. That way it doesn't rely too much on those particular perceptrons or neurons, as I like to call them. And then that prevents it from overfitting your problem too much. Though it's difficult to tune. I'll go over that too in the code, but it's you do it too much dropout and it has trouble learning at all, and you do too low of dropout and it overfits. So
Another thing about these is choosing the number of hidden layers in between the inputs and outputs, the number of layers you put in, and how many nodes, neurons you put in those hidden layers also has a lot of effect on both the memory footprint and the performance. So you play with that a lot of times too, because you might go from 64 inputs to 128 in the middle or 10 in the middle, depending upon how the data, how the signals are going to behave.
yeah, and you can really affect, like, you can very easily overfit. Like, I tried early on just putting tons of neurons and tons of layers and just seeing what that does. And what that does is it just instantly memorizes your training data. Like, very quickly you get your training data is 100% recognized, and the rest of your data is just, it's like flipping a coin, whether it figures
There's
it
an
out or
individual path that it then figures out, oh, that's this picture, and it just makes a
Yeah.
path for that. And so you don't get any, really what these things are doing is a high dimensional regressive curve fit. So if you can think of an output and an input representing a single point in a space, right? And so each one's going to be a different spot in that space represented. What this does is it builds essentially a nonlinear line that's the best curve fit of all those solutions. And so when it sees the next input, it goes, oh, that's cut that line, that's going to be this, because it's the closest to that line. If you overfit it, then it draws a line to each data point and doesn't, because an input layer, two hidden layers, and an output layer can represent any arbitrarily large order function, 45th order function to be represented in that. So they can get really precise on your training data, which is why it can overtrain.
Before we move on, can you just take a moment and explain what does it mean to kill a perceptron? I think these are all straight lines rather than just connections between them all.
it randomly doesn't use that in the next calculation, set of calculations. So it just removes that. So if you had like 50% dropout rate, it would only have, so these lines, these weights would only be active. So if I had 64 perceptrons, only 32 of them would have weights for that one value. Now it's not, I shouldn't say kill, it's like just temporarily pausing it.
So it's not
for
used
one
in the
set.
next pass, but it randomly could be used in the following pass.
Yes.
It's to force some of that memorization. If you have too many in the hidden nodes, it's to force you to have fewer so you don't memorize that next one into the new path. It's to force a couple of them through the same nodes.
Now if I had enough perceptrons, like if I needed 32 and I put 128 and I killed 50% of them, I would still have way too many and I would still overtrain because it would randomly pick enough that it would eventually learn. So killing's a bad term.
Yeah, the way you're trying is called back propagation. So you take a known output and you work it backwards through to figure out what the weights need to be to give you the inputs. And so if you've got too many, it'll just find a new pass, set all the rest of them to 0 and set each one to 1. So you want to force them in those hidden layers. You kind of want to force them to be your categories.
Mhm.
so that it forces each node in the hidden layer to be a category, not an individual image or an individual data point.
Yeah.
And then just one term real quick. So this is a deep neural network. So really the only definition of that is that I have two hidden layers. So the hidden layers are just the one between I have my output and I have my input. So my input is my data I'm feeding into it. My output is the decision it's made. And then the hidden layers don't see those edges. So it actually doesn't have to be very deep to be a deep neural network. I can have like 4 neurons, 1 input, 2 hiddens, and 1 output. An interesting thing about perceptrons too is you don't have to have a ton of them to do something. There's some interesting, we had some ideas when I was setting it up about making a line following robot or something with a single perceptron that would probably be capable of turning left and right depending on lighting conditions.
Josh, in your diagram there,
Yeah.
is this correct that each of those arrows has a weight associated with it?
Yes.
Okay.
Yeah, there's a weight. So there's a weight. These dots here just indicate that this could go down forever.
Yeah.
And then there's a single bias, and that's per perceptron. So, so that, it's interesting to me that the whole formula is just like basically W times X plus B. That is the entire formula it uses, but it does tens of thousands or hundreds of thousands of these W times X plus B calculations, and then that's how it comes up with an answer.
That's also why it uses a lot of memory.
Yeah.
Because every input has, whatever you have in the first hidden layer,
Yeah.
it has 1 B and a W from each connected node.
Yeah.
So they can get, if you're storing those as doubles, you can get
Yeah.
some memory.
So one thing that I've noticed is that a lot of the descriptions of neural networks have every neuron in one layer is connected to every neuron in the other layer. Are there benefits to having only a fraction of those connections? So that each one, for example, if you've got a 4 in and 4 out, if you have each one only connected to 2, or one connected to 4, one connected to 1, the other one connected to 3, in other words, for it to lay that out, or does that just happen with the recalculation of the weights?
Yeah, there may be, but it also may that the computer by training may determine that it's the best, because it may, after training enough data, may just set some of those weights to 0, which essentially is like severing the connection. So that
There's no
input just means
reason to
it
have
doesn't mean
it
anything.
at that point.
What?
There would be no reason to have it because it's like the dropout. With this dropout, you're going back and you're filtering it again. Whereas what you're saying is just take it out. But if you take it out, that's less data you have to base your, whatever your weight is.
Well,
So-
Yeah.
I agree
But-
with Josh's point, but I'm not suggesting that you completely take out any single neuron. I'm just saying that you might change one of the weights to 0 between one neuron and another.
You
And
can,
that is the-
it's not unheard of to use your knowledge of the environment to cluster hidden layer neurons in certain ways where you just don't connect certain neurons to certain neurons
Uh-huh.
to force some behavior.
Mhm.
But in the general case, the more like I don't know a lot about what I'm doing, or I want it to be able to be very dependable, you do what Josh and Adam are talking about, which is let it figure it out.
Mhm.
Once you've figured it out and you see in all of my test cases, these weights are always near 0, then just drop them in the real world so you don't have to eat the memory
Right.
to hold a 0.
So what I found from my experimentation, so this configuration is not really popular right now. It's kind of an old idea. But interestingly enough, this should really be able to solve any problem we have. This is a basic structure. The drawback, the reason to solve any problem you have, you would need a lot of neurons and a lot of training time. So a lot of the newer layouts are just to speed things up. It's because you only have so much time to actually do your training, and you have to do like kind of some intelligent shortcuts. I don't know, one of the new things they're doing with the image recognition, I think ResNet, Google, is it ResNet that's doing it? I think they're taking their input data and they're passing it to their next layers, and they're getting some pretty effective results. It's like speeding up training time, instead of the information like completely propagating back through the entire network. So there's lots of different layouts. This is a very simple layout, and you could spend hours talking about just all the different possibilities. I actually, in the demo, I use a convolutional neural network, which is looking at more sections of data, because I'm looking at an image. So instead of taking each input as a separate input, I'm taking clusters of like 4 or 6 inputs and putting those together because they're a section of the image and trying to find patterns.
Makes it faster.
Yeah, it really sped things up. I started out with this DNN, and it did work somewhat, but
But for
the newer
accuracy,
techniques are
you
faster.
can't- It's the data that is really the biggest concern for the way these things perform. You want to do things to make them train faster, but if your data is an issue, you're going to get crap results. Right? So if it's like you talked about, if your training data is too biased toward one type of image and you give it things it's never seen before, it may be fine. It may completely misguess. Remember the Google thing where it misidentified people's faces? Well, it's because there was some attribute of that person's face that mathematically matched a wrong image incorrectly. And so it wasn't an intentional thing. It just happened to be the training data was just too close, and it made a decision.
I think the real problem is, especially with neural networks and deep learning, is it's an environment problem. The mathematics we can do, and we can create, obviously data sets that are very resolute to whatever it is, the cameras are, and also the image coming in. But I mean, the real problem is, like he's saying, is real world application, which is difficult to impose because a lot of these environments might be noisy based on maybe, the imaging or data coming in, which could be the real problem.
Yeah, I think this algorithm is designed to be resilient to noise, so it can take a lot of that out because it's not looking at every pixel. It's kind of looking at a big brush stroke, which is why your question of more pixels will be better.
Eventually the neural networks you'll have a more like a rich database to where it's not just my data set that's been figured out, but it might be online, so there might be a database there that's always evolving based off of everybody else.
Yeah.
So like our cameras are collecting data, and we might send like a binary blob to them to say, okay, this is what I got this week, and this is the level of confidence I got, and then based off of everybody else, that might
Okay,
make things
let me
easier.
show this next part. So this is a 3 blue, 1 brown. It's the name of the videos on YouTube. So there's a series of these. Season 3 covers, this is Season 3, Episode 2. I'm just going to show a 2-minute clip. I don't want to show a big, long clip here. But if you want more information, this is like a really great series of videos. And it even goes back, if you watch the earlier seasons, it talks about the calculus and linear algebra that would be required if you really want to deep dive into the math of this. But I'm just going to show the 2-minute recap because there's some great animations of this in action, which I think really explains it. Let's see. So I set this link to start at the right time, but it doesn't work.
Biases that those hidden layers of neurons end up actually looking for.
Okay.
Those hidden layers of
Let me
neurons
try.
end up
Whoops. What happened? The audio should come out the TV, so.
Is the volume up on the TV?
Right?
we look.
There, now it started at the right spot, but it's definitely not coming
On
out.
the Windows side, like,
Give me
you're running Windows or
one
running-
Yeah.
Second to reroute the audio.
While he's doing this, you're talking about the data sets.
There you go.
There we go.
When it's like a human, it models human, so if all you see is all you ever saw was a 1994 dashboard, and then all of a sudden you saw a pickup, you might be able to extrapolate certain features of that, but if it was a 18-wheeler, you might not recognize it, because it's so far out of what you've been trained.
But how about the number of
Okay. It's not going, but we'll see.
As a reminder, algorithms is the classic example of handwritten digit recognition, the hidden layer of neural networks. These digits are rendered on a 20 by 28 pixel grid. Each pixel is some grayscale value between 0 and 1. Those are what determine the activations of 784 neurons in the input layer of the network. And then the activation for each neuron in the following layers is based on a weighted sum of all the activations in the previous layer plus some special number called a bias. Then you compose that sum with some other function, like the sigmoid squishification or a ReLU, the way that I walked through last video. In total,
I was talking about the internet problems earlier. Let's see.
Looking at the line, Josh, you're on.
Oh, okay.
But net neutrality failed.
Let's connect
Is that
to
Prezi, or is that a website you're using to host this, or is that?
Prezi, yeah.
It's like PowerPoint, but it's like PowerPoint
It's like,
steroids.
yeah, it's a little cooler.
Yeah, it looks really nice.
There are some advantages.
given the somewhat arbitrary choice of 2 hidden layers here with 16 neurons each, the network has about 13,000 weights and biases that we can adjust. And it's these values that determine what exactly the network, actually does. And what we mean when we say that this network classifies a given digit is that the brightest of those 10 neurons in the final layer corresponds to that digit. And remember, the motivation that we had in mind here for the layered structure was that maybe
Yeah, be kidding.
Suspense building time.
I know. It was only 2 minutes. I was like, certainly it can play a 2-minute video. Let's see. Whoa.
How long will it take?
Yeah. Yeah, I usually don't like using videos, but
example of handwritten digit
I
recognition.
think it's gonna get
The
stuck
whole
at the
world
same
was there.
spot if I try it again.
Because it's not.
But we'll just maybe if I go direct to YouTube, boom, 632. Maybe it's like cached by Prezi or something. That would make sense.
I would see cancer.
To watch a little video.
But cancer.
I mean, basically it comes down to finding...
Okay. And then it seems like it's spotting. So
handwritten digit recognition, the hello world of neural networks. These digits are rendered on a 28 by 28 pixel grid, each pixel with some grayscale value between 0 and 1. Those are what determine the activations of 784 neurons in the input layer of the network. And then the activation for each neuron in the following layers is based on a weighted sum of all the activations in the previous layer plus some special number called a bias. Then you compose that sum with some other function, like the sigmoid squishification or a ReLU, the way that I walked through last video. In total, given the somewhat arbitrary choice of 2 hidden layers here with 16 neurons each, the network has about 13,000 weights and biases that we can adjust. And it's these values that determine what exactly the network, actually does. And what we mean when we say that this network classifies a given digit is that the brightest of those 10 neurons in the final layer corresponds to that digit. And remember, the motivation that we had in mind here for the layered structure was that maybe the second layer could pick up on the edges, and the third layer might pick up on patterns like loops and lines, and the last one could just piece together those patterns to recognize digits. So here, we learn how the network learns.
okay.
What we want...
So that was just a quick recap of the previous episode of that series, which I really recommend watching if for a good overview of deep learning. The great animations that really bring it to life, showing what the network's doing. Okay, so that's the theory part of the presentation. On to the demo, which is going to be a little slow, so forgive me because new router and my router broke last night, so I had to get another one. So you're going to be seeing me adjust some IP addresses to make that work. Okay, so here's the my input data. So this is Adafruit, was it AMGR 8833 thermal camera. So they just have a little Learn project online, so I built that as is. I added to their project an SD card, and I put some buttons on the screen that I can press to actually save the data as images. So I'm saving the data as CSV files. I have some good data on there, so I'm going to pass this around, but if you could not touch the screen, that would be great. When I pass. So one of the problems I had was actually the camera was really slow at taking pictures, which I didn't realize at first. So I took a lot of pictures, and it would be a delay before when I pointed something it took the pictures, so I mislabeled pictures. So essentially I have buttons on. So this is actually, people know, I've had some problems with my cats making messes. So this is my ongoing quest to be able to identify cat messes. So that's the language on the screen. I kept the words short, but well, don't be offended.
When you say, sorry Josh, when you say taking images takes a long time, was it the exposure time, or is it just the...
Saving, writing to the SD card is very slow on that. Now I might have been able to speed that up or something, but...
Maybe the format you used.
Yeah, but what happens, I took 1,000 images and a few hundred were bad. So, and I'll go over the code I used to fix that problem too, because I didn't want to retake all these images. Okay, so I also have all this code posted on GitHub. It's github.com/FrankJoshua, and then it's TensorFlow demo. Why is that not coming up? CD. Development Workspace. TensorFlow demo. Okay, so I put it all into a Docker repo, like I always like doing. So you can just one command, you can start up the demo, and then you have, I'm not a big fan of Python, but I really like this Jupyter notebook. Kind of, yeah, it's really cool. Let me change things around here.
One quick question, John. What are your dependencies for running this?
I know it runs on Linux. And that should be about it.
Okay.
As always, I write for Linux.
So is it...
If you can try it in Windows, but...
You're using Python to... What is the neural network coded in? Just running TensorFlow?
TensorFlow, Python libraries. The Jupyter Notebook, or the Docker container has all the dependencies preloaded. So you just, if you can run...
You weren't running ROS or anything, or...
I am running ROS though, yes. But in a different notebook, and I'll show that too as part of the demo. Because I got really ambitious after I trained it. I was like, well, now you got to put it on a robot. I didn't put it on a robot, but I did make a device that will be mounted on a robot and that works live. So when you start up the Docker container, you just get this URL for your Jupyter notebook. So you just paste that in there. I hate that they do these tokens. There's like a security token. I really don't want security on my... I don't care about that, but everybody likes to add security in. So anyway, so these is a lot of this is junk in here too. I did some experimentations. I didn't really clean this up, but so I have P folder and my drive folder. That's my two input data, and then so I saved, my format of my data is just a simple CSV file. So I wrote, I added to this an ESP32 on the thermal camera, and I just added some code to just write the data. So these are outputs of temperatures in Celsius. So those are just degrees. All right, so that's my data. Okay, so the code to actually train is right here. Okay, so yeah, the Jupyter Notebook, if you haven't used it, it's kind of cool. You can just run like an individual cell. You can run cell one at a time, and it just, so I know right now I'm just testing that TensorFlow is imported and what version TensorFlow I have. It's a little old. TensorFlow 2 is out, but so much easier to find tutorials for TensorFlow 1, so I wasn't really ready to jump into TensorFlow 2, although I was watching a lot of the videos from the last, what is it, TensorFlow Con, or I don't know, I can't remember what they called it, but the last Google event where they talked about it.
Are the changes big?
No, they have like built-in what's called eager execution. So instead of like, you had to run everything with like a session context, and then they remove that. So the TensorFlow, it's a little complicated. You set up a graph that has like your different like multiplication values, and then everything you do doesn't happen right away. It happens later when you actually execute the training. So there's this like disconnect between the setup and the execution, and a lot of people have trouble with that disconnect. It creates a lot of confusion. So TensorFlow 2 removes that, so that seems to be a big part of it. So
Can the train be parallelized?
yes, yeah, and in fact that's one of the problems I had. So when you look at demos of how to actually do this training, everybody uses this what I call magic functions. So they have like, look, I trained on this, like MNIST is really popular. MNIST is like handwritten digits, like they were shown in the videos. So they're like, okay, I'll show you how 5 lines of code you can write a deep neural network to recognize digits. But one line is this magic function that goes to the internet, downloads the digits, reformats all your data in the right format, puts it in the right locations, and it's like, okay, well, what's it doing? Now I have my data, I have CSV files. How do I take my CSV files and put them into the right format to get them in my neural network? Like, this actually took me the longest of anything, partly because I'm not great at Python either. I'm, a Java programmer. But, and then when I look up how to do this, the second problem I run into is that most of the examples are not basic. They're now like, they go from this magic method that does everything for you to now I have this distributed network of computers, and I'm having to, divide all my data among 1,000 different computers and read them in separately, and it gets like way overly complicated. So the in-between was a little difficult. So I ended up writing my own stuff basically in just basic Python. Once I gave up on trying to do the TensorFlow way, it was actually a lot easier, because the TensorFlow way is when you need to deal with big data and distributed systems, you're going to have to learn how to read in the data the way they recommend. But for me it was pretty straightforward, so I just used, I have my file set up in, let me make that a little bigger. So I just put, for labeling my data, I put all one type of image in one directory and put a different one in a different directory. So I just walked through my input directory and split the data into a dictionary. So I end up looking like, run it again. I do have to run it. Another weird thing, it saves the output, so sometimes it seems like you ran it when you didn't, but so it creates a dictionary. So here's my dry dictionary with my list of CSV files. So that's just literally a list of names. I haven't loaded them yet, so the first step is just get a list of the names of the files. Next thing, I use pandas and NumPy to read them in. So I use pandas CSV. Pandas are a real popular library. If you're going to get into deep learning and stuff, you're probably going to want to use that. Pandas gives you a concept of like what's called data frames, which are really fancy lists that can like do things like, I don't know, give you the...
You ever done R? R has the same concept.
I haven't done R, but I know some people use it. So they're just, it's wrappers. NumPy and pandas are wrappers around arrays. NumPy is a wrapper around an array, and pandas is a wrapper around NumPy. There's a lot to it, but the basics, for what I did is I looped through all my keys in my file names, my dictionary, and then for each file name in that key, I read in the file using the read CSV function in pandas. So that turns it into a pandas data frame, which is just think of it as an array of numbers that I can now use. It's just got some interesting features that I really didn't even take advantage of, but this is just the simplest way to do it. Here I'm just filtering out the last column because I had an extra comma in there, so it was like just easy to filter that out. Then I created a list of this is my raw data I'm collecting. So I need my data, I need my labels, and then my label names. So my label names are my human readable names, and my labels were just going to be basically 0 and 1. And then that's it for my data. So what I found, then I have all this stuff, which is not, I'm going to skim through this, but essentially what I'm doing here is I only had like 1,000 pictures, which seems like a lot, but in the terms of deep learning is not nearly enough. So what I'm doing here is I'm simply, I am reshaping my arrays to basically flip my image. You think of them, they're really treated as arrays. All images are treated as arrays in this system, so even if you have an image, it's still just a bunch of numbers. But I'm flipping it and rotating it, and then down here I'm adding random noise to my image. So I'm supplementing my images with new images, because for a computer, flipping your image, doing a mirror image is like a brand new image. It would totally not recognize that if it was trained on it, or if it hadn't been trained on enough. But by creating a flipped image, I create a lot of additional data. So by doing this, I end up with
Can I ask you a quick question?
Yeah.
If you just start adding random noise to your images, how do you know how to properly label them? I mean, how do you know if it's going to, after the random values are added, that it is a wet spot or a dry spot?
you have to kind of know your data to know if that's appropriate. So for mine, I could look at it and visually see that, okay, if it was slightly colder in one spot or slightly hotter in another spot, it really wouldn't affect it. And I'll show you how I printed out and visualized my data here too, which I had to write some code to be able to do that, to make sure that it wasn't just, because if you had too much random noise, it would be junk. So they call that, you have to have some domain knowledge about the data that you're actually dealing with and how noisy it can be, and if rotating it matters. I mean, you could be training something that you don't want to recognize it as a certain
You don't want it
image if it's flipped. So, but in my case, it was fine doing that.
Yours is just blobs. So
Yeah.
that's actually better in that case.
I still have a lot of experimental code in there, so I'm just looking at the, there's a lot of, if you haven't worked with Python and NumPy, there's some weird stuff you can do that I'm not used to. It's kind of nice to do it because in Java I'd have to set up like a loop to do this
So
stuff.
much easier because Python, you don't
It
have
is.
the messaging or the
So-
text format.
I can create a normal distribution of random values, so I'm not doing very much. That's just a 0.5 variance on my temperature. A half a degree is not a lot of variance, and that's not. It's enough to make new data, but not enough to confuse everything. So when you do that, you get this array of numbers, and to add that to your data, you just you take your other array and you just add that array to it, and it just does all that work of looping through it and doing it. So
Were your pictures all on carpet, or were they on tile, and then what did you separate them?
they're carpet and rugs and stuff. And a lot of my pictures are water. I actually brought a rug and some water, so we'll show it off.
Like you call it cat.
No.
You run the cat.
The cat was behaving. It wasn't cooperating. The one time I wanted it to cause problems. So I don't know if it really identifies what I wanted to identify, but it will identify water and carpet. So okay. So then I wrote a little code here to just plot out so I could visually see what my CSV files look like and to see the rotation and stuff like that. So I'm just looping through some of my data. I just picked a range here at random. I didn't want to show them all. And then you have these, so matplotlib, you have this pyplot class that you can call and show your data, and you can format it and stuff like that. Like it kind of, so that's the CSV files when it's kind of interpolated, which for our benefit is helpful. I'll show it without the interpolation just so you can see the difference. So this is like the raw data. Now these colors don't actually mean anything. They're just kind of the color range that the computer picked. Since we're dealing with temperatures, they don't actually have colors since we can't see temperature. So yeah, it has to create something. And this is not for the computer's benefit. This is purely for me to be able to look at and verify that my data is in the range that I expect. So this is I think this is maybe an original, and then this is a rotation of that one, and this is like another rotation, and then you're getting down to some of the noisy ones. So this is noisy, but it doesn't actually look that much different than
That probably is a
normal.
really good advantage in the way you're doing that, in that when you actually have your robot, you don't know how the robot's going to approach a specific spot on the floor.
Yeah.
So it could approach it from many different angles, so training it to recognize it from different perspectives is probably a big plus for it.
Yeah, and I thought maybe I could even shift it. I didn't experiment that much, but there's probably ways to shift the angles and you get even more images.
I mean, do it like 12 times around or something. You know,
Yeah.
You've got little increments, because like I said, it could memorize, well, if I come at it this way, I can figure it out, but if I come at it from this side, I don't get it.
Yeah.
And having the images rotated would be a...
So, and when I took the pictures, I also tried to take from different angles and distances and stuff. I really wanted a variety of pictures. I bought different little rugs and pieces of carpet and stuff to try to experiment with. The more data, the better. That's one of the things I learned about this. The really improved, I mean, you could get results with just like 100 pictures, but it really improves a lot. So anyway, this is just outputting a data frame, just again seeing what my data looks like. So it's just like right now it's raw temperatures. Okay, so after that, the first process is normalizing your data. So these algorithms, they can work with any numbers, but they really are meant for 0 to 1 values. So you want to normalize your data. So there's some built-in functions to do that. Just find the minimum and maximum. So I create a min-max scaler using this sklearn pre-processing library. And then I turn my data into that. Okay, so the next part, technically, I'm going to go into too much detail. You shouldn't use all your data for the scaling. You're supposed to just only use your training data and not your testing data to scale. But in my case, I had so little data that I kind of felt it was okay to cut corners, and I felt like I'm really going to have a known range for my data too. So I think that was okay, but I'm not 100% sure.
The reason why that is you want to train on half of it, and then you want to use the other half to prove you didn't overtrain. So you've got different, when you evaluate the results of your training, you've got brand new data to use. Because if you train and then you go back and say, well, how does it fit my training data, you're not really having a good real world example. So you train on half of it and then you use the other half as the test.
So then the next part here, I have to actually save the scaler. So when I'm in the real world and I'm processing live data, I have to normalize my live data just like I normalized my training data. So I just have to save that to a file so that later in the next program that actually live scans, it will have the same setup for its raw data. Then I'm just looking at my data here, so to see what it did. So you can see it converted, up here it's all temperatures, and now it's all values, 0 to 1 values, depending on the temperature range. So next step, okay, so I need training data and I need validation data to make sure that what I did actually worked. Without validation data, you can get great results and think your model worked, and it's just horrible. So this is a method built into sklearn also that just splits your data. So I feed in my data, my labels, and my test size, which is really low. You should go higher, but again, I had so little real world data that I kind of just needed as much as I could get. But so that's 10% will be in my test. So it basically puts 90% in my training. So X is my that's actually my input, my temperatures, and Y train is my labels. So Y train is just a bunch of zeros and ones, and X train is all my temperatures, and then same thing, X test is temperatures, and Y test is just the labels, zeros and ones. Okay, so see here I'm just double checking the image to see what it looks like. That's an unformatted image. To make sure everything looked okay after I had split my test and did my normalization. Okay, so you're going to see a lot in here because I left a lot commented out because of all the experiments. I must have run this hundreds of times. I don't even know.
So you had 1,000 images? Is that?
Yeah, I got.
For you, is that total, or is that your first set of images, and then when you rotated and stuff?
No, I have 1,000 images, raw images, and then I enhanced it to it's like 12,000, I think. I think I got 12 images from rotating and putting a little noise in them, so I end up
That's pretty good.
12,000. I mean, the MNEST examples has like 100,000, so shy of, and those.
Characters that are different, so you're just looking at blobs, I think that's.
Yeah.
And you're not trying to categorize a bunch of different things. You're kind of like, you know.
Yeah, it's really a yes/no. In fact, I could have used a single output, but I was thinking about categorizing other things too. I wanted to keep it simple at first, but a little flexible.
That's where your training set has to get bigger, because you have to give it maybe 10,000 of each thing you want to classify to get a good result out. But you're kind of making a savant.
Okay, so, okay. All right, so first line is just setting up the model. Okay, I'll go back to the ResNet stuff. So, I guess I want to show down here, like, I actually got pretty good results with just this, putting like 2 dense. So this is the type. This is the first one I showed, the DNN, which just had everything connected to everything, and that was 2 dense networks. And I put a small dropout because the networks are fairly small. So I found that 0.25 with a lot of experimentations worked pretty well. So that what?
0.025. Is that 0.025? 0.5?
Yeah, 0.25 would be 2.5% dropout. And then the ReLU activation function. So that worked okay. I got like 89, 90%. Not great, but
For a first pass, that's pretty good.
yeah. Well, I wouldn't say my first pass, but my 100th pass of trying different levels. Then I tried, went to convolutional networks. So, and I didn't really talk about these, but the video a little bit touched on them. So in these, you're taking a section. So I have a kernel size. So I'm starting with 2 by 2. So I'm taking the first 2 pixels. So first of all, I'm reshaping. My model is a single array of 64 inputs. So I'm reshaping it into an 8 by 8 array. So it's more like an image to actually see on the camera instead of the raw data. Then I'm taking the kernel size of 2 for each pass. So that means I'm taking the first 2 pixels and the 2 pixels below it. And I'm going over 1, take 2 pixels and 2 pixels below it. So looking at 4 pixels at a time instead of looking at a single data point at a time. So I did that with a couple layers. So all the examples of like the really good ones, like ResNet, I was looking at how their models, they always did side by side, back-to-back convolutional networks that are the same. They like had a group of 2 and then another group of 2. So one thing they did early, or I tried, because I really tried copying them, so I had this max pooling thing. So one of the things they do is they do pooling, which if you're dealing with high-resolution images, basically pooling is for you take, so I got a pool size of 2 by 2. I'm taking those 4 pixels up top, and I'm shrinking. I'm either averaging them into 1 pixel, or I'm taking the max, the most intense pixel, and then only considering that. And so basically, it's a way of lowering your resolution. But I quickly realized that when you have an 8 by 8 image, you can't lower your resolution at all. So that was a horrible idea, and I got bad results real quick.
Is the convolution algorithm with the kernel, what does it use? How does it evaluate the kernel? Right, so you got 2x2 things, does it take the, like you said, take the brightest, is it average between all 8 pixels? Or
I'm not actually clear on that, how it actually does the math on it and how it figures it out, but so if it averages them or does a max or something. I know there's adjustments to that effect. I don't know what the defaults are, but I use mostly the defaults in this case, and they seem to work well. So at first I'm taking a small area, and then I'm doing a slightly larger area with a 3x3. So it's like looking at a small section and scanning my image, and then looking at a slightly larger section and scanning the whole image, and that worked well. I tried to go up to 4x4, and it didn't seem to help much. Probably again because
right now you're half. At 4x4, you're really half.
Yeah, that's a quarter on each scan, so it turned out to be a little much. So
if you did the other algorithm where you sub-pixelated down, I think you can go from 8x8 to 64x64 or something, and then put a bigger cell in it. You could kind of split the difference between high res and really low res. Because
did you? Oh, sorry.
Well, I had a question about your edges. Because your center sections are all going to have the same mathematical model there. But when you get to an edge, you don't have that, you can't go out farther since you don't have information there. So you're using that edge pixel only in that one instant. As you come across, pixel number 1 up here in the corner, he's in that first block of 4, but then he's gone. Okay? But pixel number 2 is in the first iteration and the second iteration also.
Yeah.
So when you simplified it, went to a 4x4 model, you didn't, I mean, you now have that edge problem on both of your data.
Yes, the edges aren't considered as strongly.
So it wouldn't add anything to your concept.
And each of those quarters is an eighth of the whole calculation, versus if you have really small pixels, it would be 1 out of 1,000 or something.
So yeah, that's probably one of the contributing factors of why it wasn't that great. So and then between these all I have the dropout layers. So 0.2 or 2.5% dropout seem to be effective, although most people recommend like 20% to 50%, but I think that's they're dealing with larger, you're dealing with a big image. I'm dealing with very, very small 8x8 is just so little data, you just can't drop out too much of the information.
16 elements, 16 nodes in your hidden layers, is that what the first 16?
Yeah, I have 16 in this one, and what I go, 4 in this one.
So you had 4 hidden layers?
Yeah, and that seemed to be faster and didn't seem to make it worse. And a lot of this was just, I mean, trial and error. I was just running it over and over again. Okay, so then after that, I flatten out my model, so that takes it from that 8x8 back to a 64x1. So it's just back to being raw data. And then I'm running it through dense neural network, very small 4x4 dense neural network for classification. So and it's hard to know what this actually does in reality, but hopefully that these net layers up here are finding features of my data. This is what I expect or hope. And then once they find features, I'm feeding those features into a small neural network, which is then classifying those features as being a particular what I'm looking for. And it did seem effective, so I think that's what it's doing, but like it's hard to know exactly what it sees or how it's working.
That was always one when the stuff started becoming a thing. Statisticians, right, so statistical analysis and AI analysis were always kind of at odds in the early days. And that was one of the big digs that pure math people had against this, is you really can't tell why it came up with the answer that it came up with. It just, you gotta believe it or not.
But it is, it's effective. So that's why it works. That's the bottom line. It did a job. I could not have done this, and it does work fairly well. If I get more data, it would work even better, I'm sure. But okay, then I have my output layer, which just has my number of classes, which is 2. So I got wet and dry, basically. Okay, so I run that cell. It makes my model. Okay. Then this is compiling my model. So this is my gradient. Okay. TensorBoard I'll show too in a minute. This is just a callback for visualizing the training while it's in progress, because it does take a while. It's kind of nice to compare when you make an adjustment between, when I'm up here adjusting all my adjustments is up here. You can see from all my comments, all my commented out lines. So I can log this information and then visualize it. They have a nice web interface called TensorBoard. Lets you visualize it and compare it to see if it actually worked better or worse. I have the gradient descent optimizer, which I didn't actually use. I used the Atom, but I did play with that early on. It was slow, not very effective.
Is TensorFlow, is it completely in Python too, or is it in something else with a Python interface?
It's Python, but I think it's got some C++ in the back end. It does some conversion.
Yeah, it always does.
Yeah. But yeah, it's all written in Python. I don't even think there's a C++
It's just
API.
APIs that they're calling.
Yeah, they're all converting it to C++.
So the meat of the algorithm is in C++, and there's
Yeah.
like a JNI layer.
So then TensorFlow would be OS specific then? Because you couldn't run a Linux compiled C++ library Windows.
Yeah, I guess it would be. I mean, I don't know.
Well, yeah, you can install TensorFlow. Yeah, it is OS specific, but I mean, essentially, it's just things that Windows would provide, like a window frame, or when you're
Okay,
creating.
this is going long, so let me move in. So here's the training data. So this is the magic. So it's actually now going through and training. So it's going through step by step. You can see up here. So this is my my loss function. My output 0.65 is kind of high. I can't really highlight that. That's the accuracy on the training data. So that's 63% accuracy, 62% accuracy on the validation data, and then the validation accuracy is 65. So as we can see, if I scroll down as it's running through different training steps, I can see my accuracy is improving. So I'm up to 82% and 85% of my validation, and it's just going up and up and up. So, and that will run for a while. I've tried running this. Running it for longer is not necessarily better for my experiment. I've tried running this like tens of thousands of epochs and running it overnight and stuff. It usually just ends up overfitting the data, so there's usually a sweet spot.
Overfitting is you graph those numbers, especially the accuracy numbers, and it'll climb. It'll be noisy, but it'll tend to climb, and then it'll take an elbow and start to climb really fast. You want to stop it right at that elbow, and that's at the point where heuristically it's not overtrained yet. But if you let it go up into that really fast rate of training, you're in the overtraining mode. Because it's kind of, okay, it's like, okay, I figured it out, I can get these now really good.
When you're running these iterations,
numbers because we only did a 90-10 split.
Right, so but if you had a good data set and, yeah.
Hey Josh, do you find any difference in running these iterations like at different times, given the fact that you're using randomization?
Yes. Yeah, sometimes you do get different results. So yeah, and I should have probably used a better split.
Noticing like the output?
Not usually that big. But
Less than 2%,
6
right?
or so.
I would assume. It's not exponentially getting larger than the randomization that you're implementing is my main concern.
Oh, you mean with the feeding in the random?
Mm-hmm.
I get an improvement from the random, but I didn't play around with the noise, if that's what you're talking about, for the images. So I think this is the last one. Let's see. If I can show this.
So that call you made in the code, dump data out for this to display, is that what?
And my last question is, you're running on CPU or the GPU?
CPU. I did not want to mess with the
To do this
GPU.
faster, way faster. I can hear your processor cooking.
Yeah, my laptop's getting a little hot running. I don't know why this isn't working. This is TensorBoard. I'm probably not going to have time to troubleshoot this. It should be showing me some data here, but it is not, so we'll skip that. But here, you can see a chart of your increase,
The graph.
a graph going up here, so Due to time, I'll skip through this.
Checkbox on top of it, show data.
Your outlier charts.
All the way up.
No, I don't know. I mean, here's an older one. So you can have different runs and you can kind of compare.
See it, elbow right there.
The accuracy.
1.0.
And yeah, some of these I have like different. They're running different amounts of steps and stuff, so they're not that great. This is one of the tips I will show of how you can spot overfitting. If you look at that orange line, that's an overfitting problem. So on one side I have the loss of my, what's it, on the left side I have the loss of my training data, and on the right side I have loss of my test data. And if you look, as my training data went down, my test data went, or my validation data went up. So that was showing that my model was getting very good at learning my training data, but getting bad at real-world performance. Okay, so let's see. This isn't real important for it to go through, but actually did go through. So this isn't actually one of my better ones, so I'm probably not going to save this. I've got around 95.5%, which is pretty good in real world practice. 90% is a little random, but at 95%, it's 5% more doesn't seem like much, but in real world performance, 5% more is.
I think industrial standards like 99%, like it's like you're not supposed to use it unless it's 99% accurate.
But
I
so.
gotta go, Josh, but I'm gonna get
Okay.
back with you on this. This is really awesome. Sorry.
Cool.
I got another meeting.
Okay, so and then I'll try to do a demo. Like this. What? Yeah. Jason was threatening, so I might hold him up on that. Okay, so this is the DNN, my P publisher. So this uses ROS, of course. Anybody who's been here before knows I'm going to use that. So I have a little demo ROS project I've set up. CD development workspace. Oh no, it's not there. Put everything in Gobbit. Get checkout tensor demo.
They start charging you for that. Yeah. The royalty for
Okay.
my name.
So I'm gonna start this. So that's just starting ROS master, and it's starting another instance of Jupyter Notebook that I can use to run my DNN. And this one has ROS added to it. And for anybody new who hasn't seen ROS, ROS is Robotic Operating System, which has basically is a messaging system for passing messages back and forth between one part of a robot and another part. So let's top a list. I should have that. Oh, yeah, of course. Like I said, the router changed, so I have to adjust my IP addresses. So this, what is my IP address? I have to get on the same network as the device. That's helpful. Okay, so 0121 is my IP address. So you guys set those as your environmental variables for ROS to recognize everything. 121. So my ROS master is going to be my laptop, which is 121. Set the IP of it. Yes. And then refresh my environmental variables. And then I should be able to start my TensorFlow demo again. And now I have my output from my ROS topic, and I have my Jupyter notebook with, since I restarted it, I have a new token, so I need to refresh that. Okay, so then there's my code. Alright, so this is a lot of moving parts here. This is a miracle to even get it working. So, so I got that. So that's my laptop that's running the master messaging bus, and it's running the deep neural network that reads in the data from this device.
What was that device?
This device is another thermal camera. This is my testing device.
Same camera as that one, just.
Yeah, same sensor. I got two of them to make things a little easier. So, new router, so I have to just put in my SSID and my password. And the IP address, which is 121, actually, that's weird, same IP address, different number. Okay, so I'm going to go ahead and load that up on this guy, which is a Adafruit ESP Feather Huzzah. And I'm just basically uploading this so it gets a new, it gets the IP address of my laptop so it can communicate with it. So that'll just take a minute. Weird quirk of this, it always slows down my port speed when I reboot. I always forget in the first one because it takes a lot longer to upload. I don't think changing it there will matter, but I'll try. So, just finished compiling, now it's uploading. I think it did work. I changed it in time, because that's fairly fast. Okay. So, now this guy is running, so we'll see. So now I should get, hopefully, a new topic, if it connects. There we go. I got my thermal cam and my P topic. So I'm going to just show that the data is coming out of my thermal cam. So now I'm getting raw thermal data piped through the ROS messaging system. So I point in my hand, the numbers get a little bigger, get a little smaller. All right.
What do you think your frames are per second if you don't have to say it?
Well, oh, you can actually tell. You type ROS topic hertz, and we can see what my frames are. So about 7.6 frames per second. Okay. Now that that's running, now I run the DNN. So, real quick, so the DNN is going to use my safe scaler. It's going to use a model. This is an earlier model that worked really well. It's like a 95%. It's going to subscribe to the thermal cam, and it's going to output the predictions of the model to my message. So, run that. Start this guy up. TF is, let's see, restart, run all. I didn't do my imports. Okay. So, now I have a new topic. Okay, so that's outputting. Now this is actually outputting percentages. So the first data, the first point in the array is the percentage that thinks it's dry, which is 100% right now, which is correct. And then the camera is, this device is listening to that message, and then it should light up if I have a...
You're not going to pee on that, are you?
Yes. So just cover your eyes if you're easily offended. And yeah, don't tell the science center I'm pouring water in their carpet, but...
That's not the worst thing. No.
Josh, you're not actually detecting body temperature, you're just detecting the temperature difference between water
Yes.
sitting
on the carpet
Yes.
and dry carpet,
Yes.
which
Yeah.
will only be different because of evaporation, right?
Or because it's fresh.
Yeah, right.
Yeah, it's fresh will be warmer. If it's
Oh.
evaporating, it'll be cool.
Hold on. I didn't have the battery plugged in. That's
Faster than that.
I'm like, why is
You
this?
just been doing all your test data with cool water, not warm water?
I've used a variety of sources,
Follow the cat around.
so we won't go into details of how or why or when I got my data, but
Trade secret.
No water, right?
Yeah.
okay, there we go. I may have to restart my
Looking for you in Forest Park.
restart manual, restart. This is a fragile system, so doing things out of order.
You can follow them on.
Okay.